Good afternoon, good morning, ladies and gentlemen. And I am Aniket from EDS Technologies, and I would be your host for today's webinar. First of all, we sincerely thanks each and everyone for taking the time and joining the session on advanced tooling method using additive manufacturing. Before we begin, I did like to give a brief introduction of EDS Technologies. So EDS Technologies was established in 1994 and is the largest technological solution provider in India with a strong focus on PLM implementation and support. We are a partner of Dassault System and have served over 2,000 customers across various industries. Our presence spans around of 11 locations in India with our headquarters in Bangalore. We also have various strategic partnership for additive manufacturing space. We have forged a key strategic alliance with global additive manufacturing leaders such as EOS and Optomec, enabling us to bring the cutting edge metal and polymer additive manufacturing technology to Indian industries. We also have collaborated with Humanetics for ergonomic solution tailored to automotive and aerospace industries, and with Technia for ensuring the product data quality. For military simulations and training requirement in the aerospace and defense sector, we work closely with MAC Technologies, SLEON, and AGM to provide advanced visual simulation solutions. In the field of GIS and location analytics, we have a strategic partnership with Esri, and for electronics design automation, we collaborated with Synopsys. We have our dedicated sales and marketing and customer support team to ensure that we meet all the customer PLM business and service requirement efficiently. Before we move to our today's speaker and technical presentation, I did like to take a moment to give a brief about NCAM and EDS Technologies partnership for promoting the additive manufacturing technology in India. So NCAM is National Center for Additive Manufacturing is a key initiative supporting the advancement of additive manufacturing technology in India. NCAM is a Section 8(1) company established by the Ministry of Electronics and Information Technology, METI, and that is Government of India, and the IT&C Department of Government of Telangana in partnership with industries. The vision is to build a comprehensive additive manufacturing ecosystem in India and to position the country as a global hub for additive manufacturing. Through collaboration with organizations like EOS and with support of NCAM, we are collectively driving the adoption and industrialization of additive manufacturing technologies across various sectors. Okay, before we move to our technical presentation, I would like to give a short brief about our today's technical speakers. So our first speaker is Mr. Arun Kashyap. Arun Kashyap holds MTech in design engineering and has over 9 years of experience in design and prototype development. Arun is a subject matter expert in prototype development using laser powder bed fusion. He is currently working as a national technical manager for additive manufacturing at EDS Technologies. Then our second speaker for today is Mr. Joe Ajay. Joe Ajay is a Six Sigma Black Belt professional and certified reliable engineer. He was awarded by the Indian Air Force for implementing India's first 3D printed flying part and by the Indian Navy for successful adoption of additive manufacturing technology in naval ships. He is currently working as a business development manager at EOS India. So now we will move to our technical presentations. Over to you, Arun.
Thanks, Aniket. Good morning, all once again. My name is Arun, and I'll be taking you to the first half of our webinar, which is the agenda for webinar today is what is 3D printing. So we'll be understanding what is basically 3D printing meaning, and then we'll be discussing about SLS and DMLS. Both are coming from laser powder bed fusion. So we'll be talking about the industrial 3D printing solutions in our webinar. And then we'll discuss some of the engineering thermoplastics that we use mainly for our SLS process. And we'll discuss about high strength tool steel material that are, I think, the one of the highlighted, I would say, topic for the webinar today. And then we'll discuss some of the applications of SLS and DMLS. We'll see the different systems that we offer and their capability. and for the webinar will be followed by Mr. Joe, highlighting the basically introduction of EOS, which is a company from Germany and providing the systems for more than 3 decades in the field of SLS and DMLS. And then Joe will be highlighting the value adds in the tooling industry, what all work has been done for past, I think, 2 decades. The tooling industry has been well embracing the concepts of 3D printing and solving the many industrial challenges. And he will be highlighting few of the real world case studies in the field of tire mold manufacturing or injection molding for pressure for plastic and pressure die casting focuses. So moving forward, let's begin with our uh, webinar. So what is 3D printing? Basically, 3D printing is a method, or we may call it a process to convert digital data into the form of your physical parts. So it may be your direct castings, or it may be your direct polymer component or metal component or a ceramic component. So 3D printing is solving a lot of industrial challenges in a very rapid way. So some people call it a rapid manufacturing process also. So the step and workflow begins with you. You need to have a CAD model with you, and then we prepare that CAD model that involves some amount of programming or CAM, and depending on different 3D printing processes. We do slicing of the model. We divide the model into detailed slices and informations, and then we send that information to the respective printer and get our job done. After the 3D printing has been done, some amount of post processing is done depending on different 3D printing processes to achieve the final component. So that's the typical 3D printing workflow that involves these stages to arrive to the final component. With EOS, we bring the technology in India, two technologies basically. One is selective laser sintering, which is melting the high performance thermoplastic materials such as nylon 11, nylon 12, and their other composites, filled composites. And on the other hand, we have direct metal laser solidification, the DMLS process, which melts the different alloys, metal alloys. The alloy can be aluminum, it can be titanium or copper, or even the high strength tool steel. So this is possible to actually get your tool that you use for your daily injection molding or pressure die casting using our DMLS process. So we'll be discussing about these. Let's understand what is the SLS process. So we have taken an illustration here of our P3 model, where you can see the dispensers are kept at top, which are full of powder, and then that powder is supplied basically, and the powder is spreaded over the platform. That is why it is called laser powder bed fusion. So we spread the powder, and then there is a laser at the top. There are heaters which preheats the powder during the process, and then the laser just select the areas. If you remember slices, we mentioned about slices, so those slices are addressed by these laser units, and just on that those points the powder gets melted and fused, and this is what is forming your actual object. And it happens in microns of the layers. So it's basically a layer wise process until your job is completed. It continues, the platform goes down, spreading happens, and the laser gel just addresses those areas. So what happens at the end of the process, we take out the exchangeable frame. We call it, you may understand it as a printing bucket. So we take out the entire bucket out of the machine, and then we take out the powder cake, remove the powder, separate the powder, and then take the usable part immediately. So right after the printing, the part are usable in the SLS process, very functional without any hassle that we'll be discussing later. So what happens to the powder after the printing is over? So whatever left out powder is there, we just sieve it so that the impurities can be filtered, and we mix it with a new powder. The mixing starts from 20% new powder to 30%, and we are nowadays able to claim a lot amount of the powder, around 80% to 70 to 80% powder is being claimed from the previous cycle and being used. So we call it refreshing. We refresh it with a new powder, and then that powder is ready for the use in the next cycle. And this makes the SLS process more sustainable, where we are able to claim more economy in producing the component. The cost per part is dropped drastically, and that is why we say the SLS process is becoming more of a production process. You can consider it. So what all kinds of needs that SLS fulfill, whether you want your prototype to be done, it will address, or if you want your functional part. So if you want to integrate any functionality, just like you want to insert a brass insert with the threads, that will be taken up by all of our thermoplastic ranges. They all of these parts are fully functional, and you can even do the testing on the SLS component. The other use case can be during your production process. You can print your fixtures, you can print your packaging, handling, attachments, or any other fixtures or jigs that are required for simplifying your process. SLS will cover all of your needs during the product development or operations or productions. So SLS is actually driven by a laser. Laser is the heart of the process, and the laser spot die is 500 micron, in the range of 500 microns. It is able to produce very detailed geometry, starting from zero point 0.6, 0.7 mm of the polymer component. You can print. So whether your component is a small scale part or a mid scale part, or a large scale injection molded part, all of the parts can be printed using the SLS processes. What amount of detail it can address? As I mentioned right before, it is able to address zero point 0.5, starting from 0.5, because the laser thickness, laser diameter is 0.5. So you can see the horizontal walls that can be manufactured. The minimum wall is ideally 0.3 mm, subjected to what is your component size overall, and vertical features that can be printed is 500 micron through the process ideally. And these are the results you can see, starting from this size of the feature to all the way to the size of the bucket. We are able to print and address today. What finish is achieved through SLS process? So right after you get your part printed, you have to take out the cake along with the powder and the component that we call the unpacking. So we seek the component out of the powder bed, and this is what is the finish achieved right after the process. So if you are okay with the monocolors, white color and black color, the SLS parts are directly usable at the first moment. And if you want any further aesthetics to be done, you can even dye them, paint them, and do the coating on those surfaces so that they become aesthetically more appealing. In any ways, the SLS parts are being used in the industry for different purposes, whether it is the component needed for aesthetic or styling or functional need or for testing. So we have got systems to demonstrate. This is our P110 system that we normally give the solution in the industry. This can accommodate 20-25 centimeter of the component roughly. And it produces, the system holistically produces more than 600 kgs of the polymer material in a year. That is very suitable for studio friendly environment, R&D and batch production, and even for sampling if you want to do sampling for your customers in injection molding. And then we have our flagship machine P3 Next, which is way ahead in the segment and produces around more than 2 ton of the plastic powder today per year. And you can imagine these machines as a daily production machines for your day-to-day plastic component manufacturing. We also have large format SLS printing. If your component is not fitting in one go in the printing volume, what is the concept we call is we need to split it and then manufacture it. We call it deconstruction. So we have large format printer with the dual lasers, which are able to address 0.7, 0.8 meter kind of dimensions in one go, and then you can imagine literally large component for the exteriors and for interior component, and of course large component in automotive and different industries. What all materials we have to offer in SLS is today we have nylon 11, all nylon 11 series and nylon 12 series for different applications. So we have pure nylon 11 in white color and nylon 11 in black color. And then sorry, we have nylon 11 climate neutral material, which almost leaves no CO2 emission behind when they are manufactured. We have flame retardant material for day-to-day applications of nowadays the EVs and the other market which want the flame retardancy features. We have direct material for that. We have composites with us. In nylon 12, we have high reusable nylon 2220 today. If you remember, the refreshing ratio I was discussing about is in this material, we are able to claim 70% of the powder from the previous cycle. And in a material called PA950HT, we are able to claim 80% of the powder from the previous cycle. Today, which makes it more economic and more it adds basically more reusability in the process and make it more sustainable in production technology. We have PS640 GSL, which is 10% lighter than the normal nylon material, and it's used for lightweight applications, and it's a carbon-filled composite material. We have glass filled material and other flame retardant material nylon 12 too, which are used for flame retardancy. We have aluminum and nylon mixture and a flexible material called TPU, which is a rubber-like material for different applications and industrial need. Most of these materials are biocompatible and they are very safe during the process, so there is no hassle in terms of operating the systems and handling the material. So when I speak about the benefit of SLS process, it has many benefits. Like you don't need any tool first of all to get your component. Yeah. Unlike other 3D printing processes, it doesn't have any support structure involved in it. So you get your direct component without support structure. Because of high powder reusability, these are more economic. There is very less post-processing. You don't have much post-processing. Immediately after the printing, you can start using it. And because there is no post-processing involved, you don't need to use any chemicals or washing processes typically done in the 3D printing. You can imagine of completely filling your printer and making each and every corner being used during the process. So that we call 3D nesting. You can directly fill the components as many as possible in this space and use the printer as production machine. And this makes it the cost per component, the cost of printing the component will be very low. We have, as I said, glass filled materials which are more robustly used in high strength polymers. We have high temperature services material and flame retardant material with us. There's no post curing, as I mentioned, not much post processing, so there is no curing, and just immediately after printing the parts are usable. There is no UV damage, and all of these materials are fully functional. So they integrate all conventional means. You can actually insert the functional inserts and make it use multiple times. So this plastic performs very well, just like injection molded plastics. We have fine detail resolution with us, FDR, which is able to address as low as zero 0.2 mm of the feature, which is used for very miniaturistic designs to be addressed and printed. And we have watertight material. Immediately after 2 mm, you can claim the water tightness on our component. So these are all benefits of SLS process. Now let's have a look at the metal printer, which is TMLS. So this is our M2 machine, and it's basically a micro welding, automated welding, which happens in an inert atmosphere, and you can directly get your castings, get your toolings done out of it. You can get your injection molded tool inserts and pressure die casting tool inserts out of it directly. We have a lot of materials to offer on it, including high strength tool materials. So as I said, it happens inside the inert atmosphere like argon or nitrogen. So the powder is fed from the bottom to top, and the recoater recoats the powder in a very fine layers as it is a powder bed fusion. And just on top, it has a fiber laser which actually melts the powder completely, 99 point, more than 99.5% to 99.6% density is achieved across aluminiums, and in steels you get 99.7% to 8% densities in your tool. So these are completely solidified materials that you get out of this printer. And it addresses very minute details. The laser diameter is just 18 microns, so it is able to print starting from 100 micron of the feature as well during the process. Immediately after the printing is done, we take out the model and put it in the furnace for relieving the stresses, the residual stresses or the thermal stresses that are induced in the part, remove the support structure, and do the desired post-processing to control the tolerances and get your functional component. So, so these materials are directly machinable. You can do EDM, you can do wire cut, you can perform, in fact, any kind of post processing. You can do even hardening after the printing is over, after the heat treatment is done. You can do further hardening process of the material to improve the surface hardness. So what DMLS for tooling industry, what we are addressing is your direct castings can be printed, whether be it a ferrous castings or aluminum castings, in a very great way. These printers will be able to print these systems. We can solve your tire molding problems. So in the tire molding, you have detailed sipes, 3D sipes, or in fact, the entire tire mold segment can be printed directly from the printer, which cut down the lead time, which cut down the hassles of manufacturing the sipes. And then we have solution for the injection molding and pressure die casting industry, where you can increase the efficiency and tool life in direct way for your day-to-day molding purposes. And this process is able to address the direct cutting tool manufacturing also. Not all cutting tool, but at least the special purpose tools and the tools which have most of the complications during manufacturing process, and there are difficulties in balancing and all. um, we the DMLS process can address those applications. I pull up one application where a company called MXC has printed the series of 36 number of cylinder heads, which are directly from the pressure die casting. So you can see the volume of the system, the printing volume, and this is what the system is. It is able to print the cylinder heads directly coming from high pressure die casting. 3D printing is producing these number of cylinders just at a rate of 1 cylinder per hour, and the cost has drastically come down, which is matching with the pressure die casting. So today, for different applications, the 3D printing processes are being optimized so that their cost can come down, their performance can be enhanced, and you can get your component real faster than the conventional process. You don't have to wait at all for your component. The second application that I told for the tire manufacturing is either you can make the sheet metal sipes directly for your mold, or you can get your segment, entire mold segment done out of it. So I'm just gonna highlight it here. Traditionally, these are the steps which you follow to arrive to your final sheet metal part. In additive way, we need a 3D model, and that's it. We can put that 3D model in a 3D printer and get that printed and achieve our final shape. So we don't in 3D printing process, actually a lot of stages in the middle stages which are responsible to achieve the features, the complicated features in the sipes are directly eliminated, and you can address any amount of design complexity from the tooling getting printed. So why AM is being used in the tire segment is because there are a lot of process complications, whether you are getting your mold, tire mold segment printed through castings. So this is how these many steps are involved in the castings, and even after this, you get defects, you get rejections in the process. And Secondly, if you are able to print through, if you are able to manufacture using the CNC, it's hell amount of time, tooling, and the energy spent on achieving the features, and sometimes not even feasible through CNC because of undercuts and other things. All of those things can be addressed through 3D printing. So this is where on the left side you can see this. There's the series of the sipes have been 3D printed using the high strength tool material, and this is the complete mold segment getting printed out of 3D printer. Both ways the DMLS can solve the tire industry need and the mold need. With this, we understand our third application, which is conformal cooling. So let's understand what is a conformal cooling basically. So you have a let's take an example of an insert. You can see this has a blue color cooling line, which is a straight cooling line, and in 3D printing we are able to actually come very close to the molding surface. So this explains itself that the operating temperature range of the tool would be well calibrated using the 3D printed conformal cooling rather than the conventional cooling, which has the limitations of drilling angles, accessibility, the wall thickness, the critical wall thicknesses. Everything comes into picture when it is conventional. So do with the 3D printing, we are able to drop down the temperature range of the mold, running temperature range, and this way the cycle time can be reduced, and the other benefits like rejections can be dropped down. So there are a lot of benefits of introducing conformal cooling concepts in day-to-day molds of injection molding or pressure die casting. So these are different illustrations I have pulled up in different kinds of inserts. You can see the complicated cooling lines, how you can actually come close to the molding surface, and this is how you can increase the efficiency. And we are able to print anywhere 0.8 mm to 1 mm to 2 mm diameter cooling channels in the inserts, and these are working pretty fine and give you a lot of benefits and payback in when they're introduced in the molds. So a lot of benefits. We'll discuss about the benefits later. Let's discuss the case study. So this is one plastic automotive plastic component we have taken, and this is the cooling network in the mold. This is the area where the problem was actually lying. There was a critical cooling condition, and the part was getting rejected on due to hotspot generating on this. So in order to improve the cooling, calibrate the cooling, the insert was replaced with the conventional line to the conformal cooling line, and this is the 3D printed insert. You can see, so this inserts goes into the tool, and the benefits, the direct benefits were the warpages were reduced, the shrinkages were reduced, the deformations that we call displacements were reduced, and the cooling time dropped down from 24 second, 35 second to 24 second, and the cycle time also overall dropped down. So around 30% rejections in this case were reduced, and productivity was increased by 20% in the plastic injection molding. So this is a great concept which is being solved by DMLS and in the conformal cooling, with the conformal cooling and injection molding. So the benefit of you can imagine estimated benefits of increased reduced cost per component approx 20 to 35%, and reduced cycle time, and improve tool life, and reduced rejection rates. All of these benefits comes into picture when we use the CFF conformal cooling concepts. In pressure die casting also, this is one example I have taken where the casting was having a great shouldering effect inside. That was a real defect during the casting process. So simulations were saying that the cooling was not efficient, and we tried introducing the conformal cooling on it, and then this complicated portion only was printed. So this is what is also possible. This we call the hybrid printing. So we only have to print the amount or the portion of the mold or the portion of the tool that is having the geometrical criticality. You don't have to print the entire mold or entire component or entire tool altogether. and the process well supports it. So we printed the complicated portion and calibrated the hardness across the mold, and it performed well. The joint were completely fine, and they were giving the high strength on at the transition also where we joined it, and the problem was solved basically. So conformal cooling is able to reduce the die life, is able to reduce the rejection and improve the performance of the overall molding process. So what material we have to offer for the direct component? We have high strength aerospace grade aluminiums and the normal grades of aluminiums for direct castings. As I said, we have the titanium, the series of the titanium materials. We have super alloys with us used for high temperature applications. We have copper alloys. We have stainless steel, the series of stainless steel, and the high strength steels to offer. So this is one example of where we are explaining the throughput of our EOS metal system. So our M290 is able to, or even in fact the other series of the materials are able to give the tons of the outputs over a year. So so this process definitely can replace some of the applications, well calibrated and well designed applications in the process, which can be proven as a production process for the metal 3D printing. So talking about material, the highlight of this is we have high strength material which directly can cater your tooling requirement, whether you want to replace your injection molded tool. So we have maraging steel, which is a martensitic aged alloy. It is a high strength material, and you can calibrate the hardness as per your need. Then we have tool steel 1.2709, which can print your tool directly. We have CM55. We have stainless steel tooling material also. And over the year, you can again imagine the tons of the steels being produced for your tooling, day-to-day tooling application. So you don't have to actually print the entire tooling from the 3D printing, but the areas which are having the criticality in terms of cooling. So with this, I would like to hand it over to Joe to take the webinar forward. Thank you very much.
Hi, Arun. Thank you so much. Please let me know if you can see my screen.
Yes,
Yep,
Joe.
we are getting the feed.
All right. Um, Good morning, everyone. I think you have had a very detailed session with Arun, and I have little content that can touch base on some of these topics for the day. And I have tailored the content as below. Number one, who EOS is, a little background about the company and what solutions that we offer, and some of our customer success stories. So EOS is a German company, and we started in '89 onwards, and we have two major products, one on metal, the other solutions are on polymer, and our metal systems dominate the market, and we are represented in about 15 countries, and we have few more partners in few other countries. So and we are near about a €500 million company, and if you see the patent history of direct metal laser sintering, and I think you can very well see that EOS was the first company to commercialize metal 3D printing for the entire world, right? Everybody started with stereolithography on polymers, but then when it comes to metal, we were the first one to market it, right? Until then, there were many patents, many research that were going on. And if somebody wants to buy a metal 3D printer, it was only with EOS. And today we are in 36 plus years, and we are located near Munich, actually, in a place called Kraling. The solutions that we offer goes this way. If you have a concept, right? If you have a part in mind and if you want to realize it, we take you through the entire path, right? We work with some of our partners to optimize the product design in terms of CAD and CAE, and then we print the product in our machines, in both polymer as well as in metal machines. And then for post processing, we partner with some of the traditional processes, where we have these sort of electroplating, so on and so forth, and some part finishing, and then you get your end product in your hand. So that's how, right from your digital device until you have the physical device in hand, you have the entire chain with us. So the solutions that we offer, of course, today, we hear that, or not today, but earlier, 3D printing was termed as rapid prototyping, and this was mainly driven by automotive market, right? This was much ahead before the product reaches the market. People were using rapid prototyping for for aesthetic purpose, for visualization, conceptualization, so on and so forth, right? Rapid prototyping fantastically driven by automotive side. But what we are seeing right now is, some of these products are being currently used in aviation industry as well as in space industry as a direct products. But then to reach the mass manufacturing, we see there is a bridge that is happening where the products are currently introduced and can replace to some extent. So, and this again is typically driven by automotive and a few other manufacturing industries such as heat exchangers, some of the semicon industries, so on and so forth, and also the medical industries where there is 1:1 manufacturing that is going on. Right. So addressing the mass production industries, typically metal products undergo die cast, right? So there is also one other industry that goes in mass manufacturing, which is the stamping. Arun have already covered how the stamping industry has some bottlenecks on realizing the geometry for tool industries such as the time mold industry. I address it on die cast industry. Now, let's say there is a product A, right? You need a quick proto, let's say within a week or so. And then typically it is done with either the 6061 material or ALSC 7mg with sand casting, right? So this is how typically within a week's time they get a part in hand. So what at EOS that we have is we have the same materials, ALSC 7mg, and we also have ALSC 10mg, which is A360, and ADC 10, which is the die cast material altogether, right? The same material which you will be die casting is currently now being also 3D printed. When it goes for pilot production, before a product is deployed or before it is released to the market, what die casters do is typically make 50 or 70 odd pieces of these parts and then have a tool that is being made for it, and they call this as pilot tools or pilot production, right? So this is typically done with a very cheap steel, and they say that okay, within 6 weeks of time you have 70 parts, so or 100 parts even, and these parts would be tested for their mileages. Basically they put it in the environmental chambers and then blast it with all sorts of corrosive media, and then see how far the material survives, right? So with this, this is how they determine the mileage of a product. Now, Arun has showed you also that we could also make such, we can replace that process just by directly printing it, right? And our turnaround time is by far one of the least of it. So it comes about a week or less than a week, even sometimes directly 3D print, and then you go for multiple processing also, such as the wire cut and then finishing such stuff. So roughly about 2 weeks time, you have 50 or 70 or 100 parts, whatever that your pilot production demands. Secondly, we also have the mass production coming in. So for that, we don't have the scalability as of today. We hope so that we'll have it. We definitely want to see much better material efficiency throughout the entire process chain in mass manufacturing. So additive manufacturing could help in. But right now, what we offer is the hot date tool steels that you can readily use and reap some benefits also. So Arun has explained you the different grades of steels, right? In plastic industry, a similar approach is also followed. Either they take a block and then machine it, or they use the material extrusion process. With SLS process for plastic, we have the selective laser sintering process. There is no support structures, which means you print, let's say, 100 grams of part, the 100 grams of part that come in directly. There is no wastages, there is no extra material that goes in as material extrusion. Directly you get it. For pilot production, typically they use vacuum casting, but then then again, this is not a one-to material that it will directly go into the injection molding also, right? There is definitely a delta that's happening there. And with SLS, you have the same material properties that you can achieve in injection molding also. And you can have multiple such products being stacked and then printed all together. So not just one or 5 parts together, but then if you want to have even short series production, then it is possible with SLS process. For mass manufacturing, similar to die casting, we have the tool steels that come in with the benefit of conformal cooling. You have much better productivity also. So I address on generic parts and then we go to tools. So these are the part properties when we compare with additive manufactured material versus the standard die cast or permanent mold casting, gravity cast, or even sand cast, so on and so forth. You can see our properties are 1:1 actually, or very close to 1:1, right? So let's say if the property is overperformed, right? So and let's say there is a customer, automotive customer who is using 3D printing and then overperforming in prototyping, right? And when it goes for mass production, you have the poorest of strength. The delta is going to be very big, so that the performance in the prototyping, let's say it's about 60,000 kilometers or so, and then when it goes for mass production, your kilometer range is somewhere around 20,000 or so. Does not match at all, right? So we tend to match the 1:1 properties. What you expect in mass production is what you need to also have in the prototyping stage. That delta is currently addressed by EOS, and here is the evidence of that you see here. The properties match almost 1:1. Now, this is a case also from automotive industry that is done for the pallet production. Job 36 parts done in 36 hours, and including material finishing could roughly come about 120 euros per piece. Now, if this has been done by pallet production, probably it is about 5,000 to 7,000 rupees. So within, for a premium that you get for 4 weeks of time, which is about 6 weeks for pallet production and 2 weeks for AM including finishing, you get a benefit of around 4 weeks that you can make use of it in your testing, right? And there is little premium. The product is not 7,500 rupees, but then it is probably 12,000 rupees, right? That premium you pay for the 4 weeks of lead time that you get. In polymer for direct parts, as I said, we have the injection molded properties being met, and primarily this is done by two materials. One is nylon 11, the other is nylon 12. And we have different filled materials in each of these categories. Some are for mineral fills as is aluminum, some glass filled, and some additives being added to have the fire retardancy and ESD, so on and so forth. So each of these fillers contribute to certain properties expected, and we have such wide variety of materials that you can use for. And if you compare the properties again, in additive manufacturing, there are two widely accepted technologies as per VDA 3405 standard, right? The one is for material extrusion, fused filament fabrication. The other is laser sintering, right? I don't say this, but the standard says that these are the two major or two widely accepted processes. And if you compare these expected properties as per this standard and EOS, properties match almost 1:1, right? And even when you compare with some of the injection molding standards for nylon 11 and nylon 12, properties are very similar. 45 megapascals that you get in injection molding, you get 48 megapascals here in laser sintering. There's marginal difference that you have it. So that is where the technology is going. Here is something that I wanted to share with you on the break-even. So let's say this is a product that we have, and this goes in little complex assemblies that are required, and sometimes very limited quantities, because not many times such a product will go into 100,000 or 1 million shots and so. So when you want to have a limited product, the cost of tooling definitely is going to be very high. Although the more the number of products, the tooling cost gets amortized, so you have the product cost come in. But then when the geometry and when the business needs changes, then you have a bottleneck of how to manage the break evens, or use a low performance tool and then keep repairing the tool. All sorts of maintenance activities come into play as well. So for such a product, what we see is when you have a short quantity such as 100 pieces or so, then probably the tooling cost is very, very high. And then when it goes in for 1,000 or so, then you tend to see that the material cost and few other costs come into play, the operational expenses that come into play rather than the fixed expenses. But for a, let's say, 1,000 odd shots or so, then probably we see a break even right about 800 pieces. So I think in those area, for such a geometry, additive manufacturing is much more economical than the injection molding altogether. So this is the way that we bridge the gap between the mass production from the proto stage. In terms of tools, this is some interesting fact that I read from NATCA, North American Diecast Association, right? So they said that of the 100 defects that the diecasters will have, is majority of them, nearly about 78% of that is contributed by the process defects, right? And remaining 20%, which can be fine-tuned, so on and so forth, all such things are by the manual interactions, right? So, and this is where we tend to see the benefits of conformal cooling. In terms of injection molding, we see the requirement is a bit different, although we don't see a direct quality being contributed by conformal cooling. Sometimes it is definitely there for a bit complex, bit large parts, thin wall geometry, so on and so forth. But when we see the larger contribution is by the productivity, by reducing the cooling time altogether, reduce the non-value add time. So one example is this that I come across, very beautifully designed, right? How can somebody design this conformal cooling geometry? Very, very complex, right? So many times people ask us, what are the design guidelines for such conformal cooling circuits, the cooling circuits? So these are our three primary recommendations. Number one, take the part contour, right? Have an offset from the part contour and have some distances. There is also a guideline depending on the material. Second is, don't have blind channels or right angles, but then have a smooth channels such that you have the smooth flow of the coolant. And not to have many such branches, but then few branches, so that you have pressure losses is also minimized, right? So three major design guidelines. We can have a detailed discussion after this call or later also to see how we can help you to design a conformal cooling cycle. And these are our tool materials currently that we have: 1.2709, the maraging steel, H11 material, 2343 coal work steel CM55, and then Corax from Wolsterpine. It's also called as EM789 material. So all such materials are available for conformal cooling tools. Some stories that we wanted to share. But before we share, another question that is often asked by our customers is, I have a complex design, right? So I wanted to 3D print. This is where we talk oftentimes. Works perfectly in a theoretical environment, but never the case in practically that we have seen. The direct design that you see is printable altogether, right? Because the product is either assembled, it has some finishing issues, such practical bottlenecks that we see while we actually work on, right? So what we recommend is, at first, look at what is the functionality of the part and then work back on the manufacturing processes, right? Everybody wants to have the theoretical design, right? Whatever the software has optimized it, we directly wanted to have it, but then there is always a bottleneck on the manufacturing. Definitely, not every process is 100% perfect. So we work back on the manufacturing process, and one of such process is additive manufacturing because it works in two axes parallelly, X and Y. We have the design freedom. That's the benefit of additive manufacturing, right? So there are also some design rules that come in, and one such design rule is the 40-degree rule, right? So anything that is below 40-degree, there's going to be a support structure that come in. Now this was a hot form tool for the A4 cars in Audi, and this is how the tool is, and they wanted to have such a conformal cooling circuit designed for this tool. Now if you see, it's almost horizontal, right? And if we have to have this channel almost horizontal, basically a pocket almost horizontal, there's going to be enough issues on heat such that you have a burnt mark such as this, right? What happens is when you have such burnt marks, the surface is very, very poor, plus the buildability is lost. And we talk in terms of 20, 40, 60 micron sizes. So even if there is some blockages there, it's going to have some issues. So we tend to avoid such burnt marks, right? So what currently the solutions that we have offered is, um, we section the part at first, right? We select different layer thicknesses where some layer thicknesses we can have a very high, we can run in seventh gear, basically highest productivity, probably 60 or 80 micron layer thicknesses, right? And when it comes to a very critical area such as this, where the channel is almost horizontal, we control the energy, also reduce the layer thicknesses, right? For a smaller layer thicknesses, to have the detailed sections, we control the energy such that it is uniform. The energy is uniform such that it does not have any stress concentrations. We typically come across stress concentrations in mechanical loading, but in additive manufacturing, we also have thermal shocks, and that could have the burnt marks. And after we have this, now we see there is not a burnt mark that comes in. The result was this: they have produced such a part. Now they have series of such parts come in for hot forming tools, and they say they are able to have the best of productivity with the segmenting of these parts, basically sectioning of these parts, and then also have new strategies for exposures, laser exposures, such that your energy is uniform, such that you are able to realize the horizontal parts as well. So this is how we define the 40-degree rule, such that you can go very steep in having such a channel. Another thing also comes from Osapine is when they did for the 789, the Corax material, right? So there are some process defects come in. Now, typically when we talk in terms of castings even, there are process defects such as blowholes, such as hot tear, things like that, right? So similar to that, in additive manufacturing also, we have such process defects that come in, for which, depending on geometry, they tend to do multiple prints, cut it, check it in lab, and see whether some process parameters has to be optimized or not, right? And what solutions that we offered was, instead of having to print it, to process it after printing, we can directly check it whether there any anomaly, the process related anomalies that happen, such that the geometry is spoiled or not. What we do is we put a camera inside the machine and then understand whether the reflected irradiation are or within the thresholds or not. I'll come to the next slide where you see how it works. And with that particular identification or monitoring method, today we can directly say, even before the part is about to be sent to lab to test it, you can directly say, okay, this part will have defect or it will not have defect, right, soon after printing. To that level, we have reduced your cost of quality. So how it works, this is called as, the tool is called optical tomography, and the hardware that comes in basically an CMOS camera, and it measures the reflected radiation, right? So basically, The process works very simple, just like the photovoltaic cell, the solar cells, right? The solar cells capture the radiation from sunlight and then produce electricity. Similar way, the laser works. Laser is also a light. It has some wavelength. It captures the wavelength. The powder captures these wavelength, and then some are absorbed, some are transmitted, and some are reflected back. Right. So ACMS camera captures these reflected radiations, and it goes very close to the wavelength of the laser, and then see whether this matches within the set threshold by the user. Right? Any outliers for this threshold is captured as an indication. Right? So there are two kinds of indications that come in. One is called hotspot, the other is called cold spot. And for each of this hotspot, we see the user will say, okay, this hotspot could be a reason for that. This hotspot could be a reason for so and so defect or so. We have had some customers have encountered some leakages, right, when they did for pressure testing. And basically, after spending near about 3 or 4 lakhs doing an industrial CT, so on and so forth, they have identified it was a missing triangle in the CAD file, right? Spent 3 4 months, 3 4 lakhs just for missing triangle of one CAD data. That's a big cost of quality. All this can be cut off with optical tomography. There is one customer of ours, MTU. What they do is they at first calibrate the optical tomography, and such that if at all they see any process defects, the process defects are for additive manufacturing, right? It's not just with yours, it is there with every other the OEMs within this technology. So they say that you need not to have the part being checked for its quality to radiography or so, but much before that, you will know that these are all the places where you can expect defects. So if your defect percentage is beyond certain limit, reject the part directly. Another interesting tool that we also offers for, especially for tooling customers, is hybrid build. Sometimes when you see a part, it just have the straight drills and does not require complex channels until the very top end. Probably you can have that particular part being already machined, fixed onto the machine, and then print only the conformal cooling segment. Right. So this is one such customer of ours, and they were able to reduce from 18 seconds to 10 seconds on injection molding. Right. And when we tend to fix it onto the powder, onto the machine should also reference it properly, correctly. Right. So for which we offer a tool called reference point calibration, where you can have a quick referencing of these parts to start the build. Some other customer stories on die casting. Toyota, along with Entity Data, they were manufacturing these compressor housings, right? And goes in 10 million shots or so. And they encounter one of the defects of die casting, which is soldering. Basically, aluminum gets stuck onto the tool. And they tried for deep drills and things like that. Even with that, they were able to reduce to a great extent, basically to half for such a defect. But then it is still has to be optimized. So with conformal cooling, now the soldering defect is zero, right? So when it comes to manufacturing, the tool does not have any soldering defects at all. Kia, they were also doing the bow pins and crankcases, so tools for those, and they had heat checks, cracks, right? And they were able to mitigate that with conformal cooling again. And then they said, if you manufacture with SKD61, which is the H13 material with in compared to the maraging steel, where you can have the conformal cooling, the life is with H13, you have somewhere around 24,000 shots, and after that, it has to be sent for maintenance. Whereas with additive manufacturing, the life is about 52K shots, no maintenance, still in the process. So that's the benefit of conformal cooling. And auxiliary tools, there are many such auxiliary tools that we also support on Polymer, but one such auxiliary tool, which is a bit interesting, could also leverage the customer input on designers on inductors, right? Which is used for case hardening. So typically inductors are made with made through the manual operations. They have sheets, they have tubes, such as standard profiles that come in, and it is a manual intensive process. And when the geometry is a bit complex, it could have these profiles are joined by brazing, and then it has to be finished. Minimum it would take roughly about 3 or 5 days to manufacture one such parts. And when multiple operators work, then it's linearly it increases. But with additive manufacturing, you could make all such parts as one single job, and you can have profiles such as the one that you see here, very complex profiles directly 3D printer. So at ThyssenKrupp, what they encountered was they had this spot heating that comes in, and when they checked for the flux density, it gets overheated, and then there is a failure there, right? And the brazing does not withstand at all. So with additive manufacturing, we had also given some inputs to them such that they can have one more round of circuit, and now the flux density is throughout the part. It's uniform throughout the part. So this is the part that you see on the left is the traditional manufactured way, where you have multiple joints, and on the right, middle and right that you see here are the printed ones where you have an extra loop to mitigate that flux concentration. So when it comes to life, typically people come to us saying that ATP copper that we get, the conductivity is so much. We have the cost of manufacturing is far cheaper. So how do we address the cost topic, right? We use commercially pure copper, which is almost which has the electrical IACS of 100%, right? Just as ETP copper, and our lifetime is 40,000 pieces, simply because we are able to get rid of the brazing. We have the uniform geometry throughout, so our density is uniform throughout, and we have much better life because of that. But here is the thing. Now, when we traditionally manufacture, because of brazing and overheating, the coils get spoiled and it comes for repair, right? And just like the injection or die-cast molds, and then there is a repair turnaround time, there is a cost to it, or sometimes the tool is completely thrown away and then a new tool is used. So that's how we have a very limited time for the tool, and then we keep giving or we have multiple tools for the same job for many pieces. But for in additive manufacturing, it's just one-time investment, and so is how we are able to amortize the cost of having multiple tools with traditional way or one single tool with additive manufacturing, where you have a uniformity in flux also. So that's the benefit that we have. Secondly, in terms of energy, if you see, because of these braces and few joints and perpendicular joints and things like that, you have a very high energy consumption, right? But when we have the similar geometry with additive manufacturing, by far we have a lower energy consumption. And if we optimize the design, this is a simulated result. We have the lowest of all energy consumption. So this is what I wanted to convey. And the summary of the topic goes like this. In terms of quantity, we are bridging the proto to mass manufacturing in pilot quantities, and in terms of even in that quantity, we are able to have the same property just as how you expect in mass productions also. And with US, we have some unique tools such as energy input homogenization, optical tomography, reference point calibrations. All this help you to reduce your cost of quality. It can enhance your quality basically, and it reduces a lot of your time, design iterations, so on and so forth. So I end my topic here, and my connects are shown here. If you have any questions, I'm here to address. If there is no time, then probably we can you can directly address it to me also. Thank you very much.
Okay, sure. Thank you, Joe. And I think uh, we are at the end of our webinar. We do have some couple of questions, but definitely we will get back to you via mail. Our experts would definitely reach out to you. So now I would like to thank Arun, and Joe for delivering a very insightful webinar today, and I am very confident it was very helpful for our audience. Also, I would like to thank our audience for taking their time out and joining this session. If you have any further queries related to the subject matter or any other requirement, you can always connect with us. Our details are displayed on the screen right now. You can reach out to us at any time and we would be happy to address your queries. Please do keep an eye on our upcoming seminars and webinars. You can follow us on our social media for the same. Thank you, everyone.
Thank you. Bye-bye.
Thank you. Have a good day.